Welcome! In this video I will talk about the so-called ROR bug of early 6502 CPUs that were produced before June 1976. It turns out that these CPUs don't have a buggy implementation of the ROR instruction, but are missing the instruction altogether on the silicon die. This can be proven by a missing circuit that could transfer the carry flag to bit 7 of the accumulator. Without this circuit, ROR is impossible to implement. Let's have a look what happens if we use the instruction anyway. For this I have prepared some machine code programs. I have entered a program from memory address 310 to memory address 320. And what this does is it loads the accumulator value from memory address 300, clears the carry and perform a rotate to the left. So the opcode 2A here is rotate to the left. And if we execute this command, so this assembler program, let's say 310 run. So first we have to set a value in memory where it loads from. So let's set the value 44 and then execute the program on address 310. And now we can output the memory values from address 300 to address 302. And as you can see, the rotate to the left value is stored correctly to the memory address 301, namely 88 hex. So 44 hex rotated to the left is 88 with cleared carry. The same program can be executed with the ROR instruction by changing the 2A to 6A. So on memory address 314 I will enter the opcode 6A and once more run the program. Show the result, and as you can see, the result is exactly the same, which should not be the case. So this means the ROR instruction behaves the same as the roll instruction, or at least the arithmetic shift left instruction. Up to now we cannot tell anything about what happens with the flag register. I have entered a second program at memory location 330 to 340. Sorry. Oh. Now come on. Stupid keyboard. Here we go. And here we have the difference to the first program. We have 38 here, which means set the carry flag. So the carry flag will be set before the ROR instruction is executed. The rest of the program stays the same with 6A, meaning the ROR instruction that is supposed to be buggy. The input value is the same as before, 44. So now let's execute the program from address 333 and examine the memory from 300 to 302. And as we expected, it behaves the same as before, so the carry flag does not have any impact. However, if we replace the opcode 6A with the opcode 2A, so making a rotate left instruction at address 334, we input 2A and re-execute the program and dump the result, we get 89. This is expected as the roll instruction should really shift in the carry from the right correctly. So bit number 1 gets set. So this is the proof that in this faulty CPU the ROR instruction behaves like arithmetic shift left. However, we have other addressing modes that can be tested as well. So the 6502 CPU has a special addressing mode using the index register X. This example program on address 350 hex first sets the index register to a value of 0, then loads the accumulator from memory address 0, stores it into the memory address 1, and then performs the rotate to the right instruction on the index 0 page, hex 1, X. Then it pushes the processor status flags onto the stack, gets the accumulator from the stack, thereby setting the accumulator contents to the status register contents, and then stores the accumulator to memory address 2. Then it clears the carry flag for being tidy and then returns to the Bosniak monitor. And if we now execute this program at memory address 350 and we now print and again the input value was at address 0 and the result is now on address 1 and it is 43, and the same goes with address 300. This is the input value for the next program. So program number 4 is exactly the same as program number 3, except that the addressing mode for the ROR instruction does not refer to the 0 page indexed by X, but rather to a 16-bit address. So having the full 16-bit address range of the 6502 addressed by the index register X. At 380, and when we execute this, we also get 44, 43, 30. And if we want to replace the ROR at address 389, we have 7E, which is ROR address, X. And if we want to replace this by roll address, X, we must enter here 3E, and then we can re-execute the program and then examine the memory, which turns out to be 88. So this actually works, which has been proven here, but the ROR does not. It produces 43. And we can also check the program at 357 and 357. We have 76. If we replace this by 36, and again at memory address 0 we have 44. If we now run the program at 350, examine the memory, we get exactly 4488B0. So all the programs run correctly with the roll instruction, but with the ROR instruction the result is wrong, but differs from the ROR instruction directly acting on the accumulator. So let's summarize. We have seen that the rotation to the right of the accumulator behaves exactly as the arithmetic shift left of the accumulator, since when setting the carry flag it doesn't have any effect on the result but stays unaltered in the flags register. However, rotating to the right operations on any indexed memory mode somehow inverts the low nibble bits, but it is unclear what happens with other values than 0x44. We cannot deduce any valid pattern yet. We have also seen that the roll instruction in indexed memory modes works perfectly. Thanks for watching this video. I hope I see you in my next video.